Welcome back to Abstract Algebra. Today we're going to talk about P primary components. Why? Because remember that our goal right now is to prove what we call the fundamental theorem of finite abelian groups, which is a classification theorem for finite abelian groups. And the way we're going to prove it is by decomposing our group into direct product of P primary components and then prove the theorem for each P primary component. So let's see what a P primary component is. First, a reminder that in the previous video, we defined P group. So if P is a fixed prime number, we say that a group G is a P group if every element has order a power of that one prime P. And we prove that, in fact, a finite abelian group is a P group if and only if the power of the group is a power of P. And we also prove something important, which is a special case of Cauchy's theorem, which is that if you have a finite abelian group of order n, then if a prime divides the order, then G contains an element of order P. So let's go ahead and define P primary components. So here is the definition. Let G be a finite abelian group and let P be a prime number. The P primary component of G is the subset of all elements of G that have order equal to a prime power, equal to power of P. So we're going to denote that P primary component by GP, and it is every element of G such that the order of G is P to the n for some n bigger or equal to 0. And the first thing we're going to do is, well, let me give you an example of this. So for example, if I have z modulo 6, then there are elements of order 1, 2, and 3 here. So we have, if this is G, then the two primary component here would be elements whose order is a power of 2. So we have 0 has order 1, that is a power of 2. And then elements of order 2, 3 has order 2, and that's it. So this is the 2 primary component, while the 3 primary component is 0 has order 3 to the 0, 2 has order 3, and 4 has order 3. So these elements form the 3 primary component. Note that 1 and 5 have order 6, so they are not in the 2 primary component or the 3 primary component. And by the way, if P is not 2 or 3, the P primary components, it's just 0. The only element in any of those other P primary components is just identity. Okay, so let's prove that the P primary component is actually a subgroup of G. So here is what we want to prove. Let G be a finite abelian group, and let P be prime. Then GP, the P primary component of G, is a subgroup of G. So let's prove that. First of all, note that E is in G, and E, the order of E is just 1, which is P to the 0, and that tells me that E is always in the P primary component for any P. Great. Second, suppose that G is in G, then in fact in the P primary component, then by definition the power the order of G is a power of P for some n bigger or equal to 0. And we have a formula for the order of the inverse. The order of the inverse is the same as the order of the element itself, so it's also P to the n. So G inverse is also in the P primary components. So P primary components are closed under inversion. So what about now if I have G and H in the P primary component, then I want to know what is the order of G times H. I can actually figure that one out, but let me just say, suppose that G is order P to the N, H is order P to the M, then what happens, for example, if I do GH to the power, so I'm not looking at the order, I'm just going to do this to a power of P to the N plus M. Then to that power, I have, for example, I can write this as, because in fact in here this is important, that G itself is a billion. This will be G to the P to the N plus M times H to the P to the N plus M. Note that that is not true if G is not a billion, but because it is a billion, I can do this, and this is, so this is the same as G to the P to the N times P to the P to the mth power times H to the P to the mth power to the P to the nth power. And this, since G has order P to the N, this is the identity, and H has order P to the M, this is the identity, so this is the identity. And therefore, since the G times H to a power of P gives me the identity, that implies that the order of G times H divides P to the N plus M, and therefore the order is a power. I don't know exactly which one. You can figure out actually which one it is, but it is a power of P, and therefore GH, the product, is in the P primary component, and therefore these three things together tell me that the P primary component is a subgroup, because the identity is there, it's closed under inversion, and it's closed under multiplication, so it is a subgroup of G, and I'm done. Okay, so now what I want is our theorem, which is that a finite abelian group is direct product of P primary components. So this is the theorem we want to show today. Let G be a finite abelian group with, I want to see what is the size of G. I'm going to factor it, is going to be some n, but it's going to be P1 to the A1 times P2 to the A2 times PR to the AR, with each one of those are different primes, and each one of the exponents are natural numbers. And then G is isomorphic to GP1 cross GP2 cross GPR. So it's the internal direct product of all of those, where each one of those is the PI primary component of G. Okay, so this is an internal direct product. And we talked about the internal direct products in the past. So what we have to show is one, that each one of those is a subgroup. we have done just that a moment ago. We've proved that P primary components are subgroups. Two, we need to show that their intersections, if I is not J, then the intersection of each one of those components is just trivial. Three, we actually need that all of those components commute with each other. So if G is in GPI and H is in GPJ, then GH is HG. That's one of the conditions for an internal direct product. In here, the group itself is abelian, so this is automatic. And four, we need to show that G itself is product of all of those. So, i.e., that if I have an element G, I can write it as a product of elements, each element, each of those elements in the P primary component, in the corresponding P primary components. I need to prove all of these things. So let's go step by step and prove all of those. Here's the proof. First, the fact that this is a subgroup because GPI is a PI primary component. And those are subgroups by the previous proposition. So that is true. Two, let me get out of the way the commutation, the fact that elements commute. So if G is in GPI and H is in GPJ, then GH is HG because G is abelian. So that also works. Three, I want to show that these components are disjoint, and I'm going to do something better. I'm actually going to show that let's just for the sake of just without loss of generality, I'm going to show that actually the first one intersect with the subgroup generated by all of the other ones, which is of course does contain GP2, for example, that this is just E. Okay, so let's show that that is true. As I said, so for example, if I want to show that that is the identity, I can show, if I can show that this is just, the intersection is trivial, then the intersection of these two will also be trivial. So let me show that this is trivial as follows. Suppose that I have something in here. If I have an element in here, then it is in GP1, so there will be some, let's say, G1, and it will also be in the product of all the other ones. Since everything commutes, I can write it as a product of elements with each one of those is in the corresponding P primary components. So suppose that happens. Then notice that the order of G is the order of G1 is equal to the order of all these elements put together. But the order of G1 is a power of P1. So there is some power of P1 to the N1, let's say, that has to be equal to the order of this element. But the order of this element, the order of this is a power of P2, the order of this is a power of PR. So the order of this is a product of powers of primes from P2 to PR. So this has to be something like the order of the right-hand side is something like this. But now these are all distinct primes. All the primes are different, And we have the fundamental theorem of arithmetic. So now I have an integer that can be written in two ways as product of primes, and those are different primes. But the fundamental theorem of arithmetic tells me that this has to be the same factorization, and there is only one way that this can happen, only if this is 1 and this is 1, and therefore the order of G is 1, and that implies that G itself is the identity. So there is only one element in that intersection, and that is identity, and that's what I wanted to prove. So now the last part we want to show is that G is direct product of, that actually I can write any element in G as a product of elements in the P primary components. The last bit we need is to prove that G is an internal direct product of the P primary components. We need to prove that every element of G can be written as a product of elements in the P primary components, i.e. that if G is in G, then G can be written as G1 times G2 times GR, with each one of those in the appropriate P primary component. So let's do that. Let G be in G with order of G. What? Well, remember that the order of G is P1 to the A1, PR to the AR. So the order of G is some also some product of powers like that. The order of G has to divide the order of the group. So this is P1 to the beta 1, PR to the beta R. All right. So now defined. Now let I'm going to call them alpha i's are going to be the order of the group divided by the power of pi to the beta I. And notice that this is some integer, and that is because, well, p1 to the beta 1 does divide the order of G, so this is an integer, and I'm going to call that alpha 1, say. Okay, so I have alpha 1 through alpha r. And notice and note that the GCD of those alphas, alpha 1 through alpha r, is 1. Because, well, if something divides everything, well, alpha 1 is not divisible by, alpha 1 is not divisible by any power of P1. But alpha 2 is not divisible by any power of P2, and alpha 3, and so on. So there is no common factor. If one prime divides alpha 1, it has to be one of these, but there is some other element here that is not divisible by that prime. So the GCD is 1. And when we have elements or natural or integers that the GCD is 1, we can use what we call Bezout's identity, or a generalized version of Bezout's identity, to show that there is got to be integers b1 through br, integers, such that alpha 1 b1 plus alpha r br is 1, that I can write a linear combination of the alphas that gives me 1. Okay, so why is that helpful? Because then I can write G, which is G to the 1, as G to the alpha 1 b1 plus alpha r br, and that will be G to the alpha 1 b1 times G to the alpha 2 b2 times G to the alpha r br by the laws of exponents. But what about each one of those elements? Why do I like those elements? And note that G to the alpha I bi, if I raise that to the power pi to the beta I, then what happens? Alpha I times that power of p, alpha I times this power, is the order of G. So this is G to the alpha I pi to the beta I to the bi'th power, and that is G to the order of G to the bi'th power, and G to its order is the identity, so this is the identity. So you see now that each one of those elements, each one of these elements, has order a power of pi. So each one of those elements is in the in the P primary component that I want. So what I've shown is that G is G to the alpha I, or G to the alpha 1 B1 times G to the alpha 2 B2, G to the alpha R BR, with G to the alpha I BI belongs to the PI primary component, and therefore this thing G is written so that it does belong to GP1 times GP2 times GPR. And that shows that G is the product of all the P primary components. And that concludes the proof that G is then internal direct product of its P primary components, GP1, GP2 cross GPR, which is what I wanted to show. Okay, so we are done here, and then now what we're going to do in the next video is to show that each one of these P primary components satisfies the fundamental theorem of finite abelian groups, and therefore all of G will satisfy the theorem, and that will give us the big theorem. Okay, so we'll do that next.